to start the last seminar before summer comes to Northern Hemisphere. And we had a last-minute cancellation, and we're about to cancel this last seminar. But fortunately for us, with a recommendation from Francis Macdonald, we contacted Kurt Sundell, and he agreed in last moment to step in. So be kind of gentle. He just got from the field where he taught field school, and on the way sort of traveling to our destination. So he basically prepared it in the last moment. And after this seminar, we'll take a break. So Alex and I wish you good fieldwork if you're doing fieldwork this summer, or if you're staying home, I guess writing papers. So with this, it's a pleasure to introduce Kurt Sundell. Kurt did his undergraduate, and I presume originally from California. He did it in University of California, Davis, and when he moved for master degree to University of Kansas, where he studied what seems to be main focus of his research, working on basin analysis, and specifically on relatively recent tectonically driven basins, like in Tibet, related to collision Asia and India, and in South America. And he spent a couple of years working for oil company Schlumberger, and I guess found that it's not his love. Returned back to academia to do a PhD in University of Houston, again working on basin analysis and applying geochronology, detrital zircon geochronology in South America. And then he followed with a postdoc at University of Arizona for 3 years, until in last year he stepped in an assistant professor position in Idaho State University. And he will talk today about global records of hafnium isotopes in zircon, shedding light on Earth's deep past. And I understand it's part of the paper he published with Francis Macdonald, and there is another paper in preparation. So probably his talk will be drawing from both of these papers. So with this, pleasure to pass it to Kurt. Kurt, take it.
Let me unmute myself. Can you hear me okay?
Yeah, you're good.
Great, thank you. And thank you so much for putting together this kind of virtual forum that you've been doing for some time. And thank you for everybody for tuning in. And also again to the UCR folks for, I don't know, call it taking a chance on such an early career person giving a talk in this forum. So I really appreciate that. A bit of a quick backstory. So as Audrey mentioned, most of my graduate work, all of my graduate work really focused on the Cenozoic, and a lot of it kind of the late Cenozoic. And it really wasn't until I started my postdoc with George Garrels down at Lasercon, I started getting into this like deeper time, sort of these deeper records. And that's about the time Francis came out and gave a colloquium talk. We went out to lunch, and the rest is kind of history. We've been working on this for, gosh, whenever the pandemic started, before that. So sometime. So I'm really excited to talk about what we found. And really the deeper I go into these early Earth records, the more excited I get about it. So again, I'm really excited to give this talk. And so global records of hafnium isotopes. Click on my screen here. There we go. So some objectives of this talk. First, it's kind of a two-part talk, really. I'll talk a bit about methods and then application of some of these new methods that we've recently published. And as Audrey mentioned, I will go into what we're working on right now. So first I'll describe some of these new data visualization and interpretation methods, specifically for hafnium or really any bivariate data. Really, this was an exploratory investigation at first when I got into this sort of work. Now it's very much hypothesis driven, as you'll see. And so we'll dig into both igneous and detrital zircon, uranium, lead, and hafnium data. And really the big test here is, the question is, are these global hafnium records representative of kind of wholesale phenomena, right? So when you take these large compilations, are they representative of Earth processes that are, again, wholesale, so the entire Earth? And let me get my pen working here. Oops. Let's see if this will work. Okay, great. And really, a lot of the work leverages work by Steve Putz. He's out in Hawaii. He really did the big uplift of taking these global records and adding the critical metadata of geographic location, right? And one of the major questions in this talk is this, what I'm going to term this isotopic excursion in the latest Neoproterozoic, is this, again, one of these wholesale records? Is this something that is a global Earth process, or is it a localized record associated with tectonics? So zircon, certainly one of my favorite minerals. We'll talk about zircon from igneous rocks and also from detrital rocks. We won't focus much on metamorphic rocks today, although the way the database is set up that I'll talk a lot about, we can't really tease that out because whether the detrital samples have these in them. But we'll focus on both of these rock types, right? So detrital and igneous. So I'll separate these out for part of the talk and then I'll bring them back together. So a quick primer kind of on hafnium isotopes. The ratio of interest for hafnium is this ratio here. So 176 to 177. And this is because hafnium 176 is the radiogenic daughter product of 176 lutetium. The rest of the hafnium isotopes on this chart are stable. And this is extremely fortunate because notice there are 3 different masses of 176. So when you measure zircon on a mass spectrometer, it can only tell you the mass, right? It can't tell you whether it's lutetium or terbium. But we can use these stable ratios of these stable hafnium isotopes to correct for that isobaric interference. So again, the 176-177 ratio is what we're interested in. And this is an interesting ratio for several reasons. So this is a chart going from basically covering all of Earth history, showing different Earth materials, and that 176-177 hafnium ratio through time, basically how that evolves through time, right? So imagine, say you're a mantle peridotite and you form at, say, I don't know, 3.5 billion years ago. You have a lot of lutetium 176 in you, so you tend to increase through time, right? As that 176 lutetium decays to 176 hafnium. Similarly, but not as dramatic, if you take like average Earth crust, right? So continental crust, say like a granite, it has less lutetium 176, but it still has quite a bit. And so it will evolve along a trajectory like this. Zircon is special. It's special for a lot of reasons, right? It's kind of like Earth's geochemical kind of time capsule. It doesn't have a lot of lutetium in it. So when it forms, say, again, let's take that kind of 3.5 billion years ago, because it has very little lutetium 176, its ratio really doesn't change all that much. And this is extremely fortunate because we can then use this 176-177 initial ratio upon crystallization and say something about the melt in which that zircon formed. Now I know I have a terrible memory, so I can't keep these numbers in my head very, very long, maybe tattoo them on my arm or something. But what we tend to do here is, and most people tend to interpret the data this way, they'll take this chart and they will normalize it to the chondritic reservoir. and sort of turn the whole thing on its side. And so if we do that, now we have what we call epsilon hafnium T. So this is initial hafnium at the timing of crystallization. And this is useful because we can then analyze a zircon for its uranium lead date and ascribe an age, and from there interpret the hafnium value at that timing of crystallization, so initial hafnium. Right, and most of the, you look at Fernando Beo's work and lots of other geochemical work, most of the hafnium in Earth's crust is locked up in zircon. It just fits in zircon, one of these incompatible elements that very late stages fits right in. And so in order to get more evolved zircon, call it more negative zircon, you need to melt older zircon, right? So that's a critical point that I'll hit here in the next couple of slides. We can ascribe some jargon. This isn't the best jargon in the world. We actually changed it in the paper sort of last minute on recommendation, but we'll call for this talk, because I have the slides ready, we'll talk about these in terms of juvenile. So plotting near the depleted mantle line. So basically extraction from that mantle. Or more evolved, so incorporating more of that older continental crust, really those older zircons that have that hafnium in them. And this jargon is useful to, so we can relate these different kind of zones in hafnium space to tectonic context, right? So how do we get juvenile initial hafnium? So what we need is young crust, young zircons, and incorporation of primary mantle, right? The way George described it to me once when I was still a postdoc, it's kind of you think of it like a Libra, like how much old crust do you incorporate versus primary mantle? And that's kind of a balance, right? How much is incorporated in that melt? So if you have a tectonic situation, like say a continental rift of young rock with incorporating young rocks, or say some Cordilleran origin like this, like the Pacific kind of ring of fire that we have today, you'll get very juvenile initial hafnium. So how do we get evolved hafnium? So evolved hafnium, we need old zircon, right? We need, so that zircon can be locked up in some old crust. So you have maybe some crust away in Texas, you have some subduction zone that melts and incorporates some of that old crust. Or you have old zircon locked up in an ancient or a passive margin that contains detritus from some Archean or Paleoproterozoic terrain, and then you subduct that. So that's kind of the recipe for getting more evolved zircon hafnium. So ever since there have been large compilations of these types of geochemical data or dates, there have been big tectonic ideas that have followed, right? And here's just a couple of, or a handful of screen grabs that I pulled from controversial maybe work, but just exciting ideas, right? Big ideas. So this classic paper by Sobolev and Brown. So how much does surface erosion of these, of the different terrains, how much does that act as a lubricant for actually, either kickstarting or ending plate tectonics as we think of it today? Or we're all familiar with Warren Hamilton's work. So, when did plate tectonics as we see it and observe it today, when did that actually start? Did it start very late in the Neoproterozoic, or was it earlier? Big topic of discussion. It seems like it's really even picking up more steam right now. There's a lot of excitement behind this. And if that's the case, what preceded modern plate tectonics, right? So is it some single lid, this kind of stagnant lid that Bob Stern talks about? So it's these big ideas. And in a similar vein, Brennan Keller's recent work on the Great Unconformity. So what happens when you have a snowball Earth and you erode 3 to 5 kilometers of that, as they call it, the continental freeboard in their work? What happens if that actually took place? And is that the driver of this major hafnium isotope excursion that we see? So a couple of examples. So here's again that Sobolev and Brown paper. So what a lot of folks do is they'll take the global record, right? And they'll take some kind of running average, sometimes compare it to say strontium, and then put it on these charts that incorporate all kinds of different of data and make some major tectonic interpretations. So here I'm going to try to highlight this. So here's the Hafnium kind of running average for all of the data that was available at that time. I can't remember how many data points there are on this incorporated in this graph, but what you see is that major pull down. And again, the question is this a global process, right? In this case, related to these major lubrication events as they discuss. Another interesting use, here's Brennan Keller's work. So a lot more data that they compiled. It's data compilation upon data compilation upon data compilation. But what they do is they take an approach where they say, well, let's treat all of those data as the prior, and let's resample this the existing data inversely to data density. So what I mean by that is basically sample the troughs more than the peaks. And you'll get a posterior data set here of 10 to the 7, what's that, 10 million data points that they say is more representative and of the actual record, and make some major interpretations with the posterior rather than the prior. So a couple of examples of how people have used these global records. But the problem with a lot of these is until really Putz and Condi in 2019 and Steve Putz's recent 2021 paper, these don't incorporate geographic or geologic context, right? There's no GPS coordinate, and that's I think that's kind of an issue. And so I'll really lean into that for this talk. Let's talk a little bit of methods first. So bivariate kernel density estimates are used all over the physical sciences. I feel like they're a little bit late to the game for Hafnium data. Chris Spencer's put out a handful of nice papers where sort of introduces them, and I've been using them extensively since I've discovered a mathematically easy way to make them. So the idea here is that, let's say we have a data set here, so n equals 1, so not a very large data set. And we turn the x and the y axis into kernel density estimates. And for a KDE or kernel density estimate, you ascribe an arbitrary bandwidth to these data. And usually you base that like on uncertainty. These are huge bandwidths just to sort of show what's going on. But mathematically, you can convert that into a 3-dimensional Gaussian curve. And so what we're actually looking at here is it's basically a little mountain, a little volume, right? Excuse me, where peak density is right there on the top. I apologize in advance for our friends out there with color blindness. I have stopped using this jet color ramp, so it'll be a mix for this talk, but I've gotten rid of that. So if you can't see the difference here, I apologize. But anyway, so this is what we're looking at. And when I first started trying to make these, basically you make a 3-dimensional Gaussian for lots and lots of points and you add them together. But there's a simple mathematical trick with, I'm not going to go into the math, but to make this actually very quick, and you can do it for tens of thousands of data points very quickly. So, and so if you don't feel like figuring out the math, I've done it for you. If you want to use this this little program that I made when I was a postdoc. And so this will produce these sorts of plots very, very quickly. And it's actually, George always would give me a hard time. He says it's a very fun procrastination tool. So you can click through the different color ramps and things. And I've incorporated the different evolution lines, depleted mantle, chur, and that sort of thing. So if you're interested in that, you can always reach out to me directly or just check out that GitHub page. But this is this plot. So I made this using this Hafnium plotter software and bivariate kernel density estimates. And really, this is the plot that got me excited about deeper Earth time. So I was a postdoc trying to publish my first paper, and the most exciting thing we found was in this latest Neoproterozoic was this major pull down. And I had only really studied Cenozoic rocks up until this time, like, hey, what the heck is that? Right. And so, we made some interpretations. This is data from the Central Andes. These are Cenozoic sandstones from the Altiplano, on the other side of the Gondwana and Suture back when it was a supercontinent. So, hey, how did that happen? Right. And so this really is what got me excited about deeper Earth time. A big part of my PhD work, I focused on quantitative comparison of detrital zircon data. And so what I really wanted to do was take those bivariate kernel density estimates and figure out a way to quantitatively compare them. It's very easy to look at a bunch of wiggles or a bunch of these density plots and make an interpretation, but it's easy to be subjective. And I'm guilty of it. We're all guilty of it. It's that you want to test your hypotheses. And so for what I will call one-dimensional data, it's very difficult to compare or you'll get a non-unique result if you have the same age peaks, right? And this is really where Hafnium data is so powerful, right? Because you can discriminate between these two, call these like sediment sources or something like that, where the second dimension of data will tell you something more than these non-unique age peaks, right? And we can turn these into bivariate kernel density estimates. And once we do that, we have a Z axis dimension, which we can then use to create and call it an ad hoc comparison method. All right, so in a 1D sort of sense, say you have some detrital zircon data, you just have age, and really it's just an array of numbers of y-axis measurements, right? And so all you have to do in the detrital sense, these aren't functions, they're just discrete points, right? And so if you take every point along the x-axis, right, every point along the x-axis and just multiply them together and then take the square root, that's the geometric mean. It's actually and then if you add those all together, you get a number between 0 and 1 that tells you, hey, how similar are these, right? So it's an objective way to do this. And people have been doing this in the detrital zircon game for some time. Will Amadon really was a pioneer here. George, of course, was in the game early on. But this is what's called a Bhattacharya coefficient, right? So this math has been around for a long, long time. So what my PhD advisor and I, so Joel Saylor here, we got really excited about this. We said, hey, let's try this in a two-dimensional sense. I remember drawing this on a napkin at a GSA forum in like 2017 or something. It took us a minute to publish it, but we finally did it. So I'm going to skip over that. And so here's a really coarsely discretized bivariate kernel density estimate, just so I can sort of explain what's going on here. But it's the same idea. Take every cell, call it, multiply that Z value, and then take the square root, that's the geometric mean. Most of these are going to be zeros, right? You go along the rows, you go down the columns until you hit something where you actually have some higher magnitude, right? Here, multiply these guys by these guys, you're going to basically get 0. But if you multiply these by these, then you're actually going to get something. And what you get, here's the math in 2 dimensions. It looks very similar, but you can see that the number's a lot lower. But critically, and for this talk, what I'm going to lean into is you'll get a map from this data. You can actually plot this. And so you can get a visual assessment of the comparison of these two bivariate kernel density estimates. And this is what hopefully I will convince the folks out there that this is a useful tool. Whether you boil it down to a number or you actually get a map of where in Earth time are you similar and different in Hafnium space. Okay, so on to the global database. Again, we're going to leverage work by Steve Putz. Really, that is the legwork that's been put into this. So here's the global database. So Francis and I went back and forth on this several times on how do we actually even just separate out the data. You start with different continents. You say, well, breaking things out by the 7 continents doesn't really, it doesn't incorporate the geology. There are these, as far as geoscience is concerned, there are these arbitrary boundaries. So what we did, we took Demir and Torsvik's 2014 paper and we separated out, call them 8 continental zones of based on Paleozoic sutures. So we have a lot of, we have the continents, the kind of standard continents that we know and love, but we also have a couple of weird ones. So we have Baltica, right? So basically, Scandinavia and Eastern Europe. And then we have Peri-Gondwana, right? So basically all of the little continental fragments surrounding Gondwana when we reconstruct that supercontinent, right? And this turns out to be, we think, a better way to look at these data and separate out, parse the data to look for different trends. So here's the actual database. So we have, the zoom is in the screen is in the way. I think it's 155,000-ish points. And so what we're going to do is make a bivariate kernel density estimate for each of these different, call them continental zones. But first we can look at the data just purely based on density. Here's another bivariate kernel density estimate, but based on latitude and longitude, right? And this is I think this is a very telling plot, right? So think back a few slides ago, the kind of running average. If you took a running average of all of the data, are you telling a story? Does that trend tell you a story about wholesale Earth process? Or are you really talking about mostly data coming out of China, South Africa, South Central Australia, where we have most of the data? So the warmer colors here, hopefully this is a color scheme that works better for color blindness. So perceptually uniform color ramp. So these zones, I think you're telling more of a story about those zones rather than say, are you saying anything about Greenland or North America is very sparse in comparison to the amount of data in that Asian continental zone as we've demarcated it. So it's a story of bias, right? So these are some weird looking plots. I'm going to take a minute on this slide. In the last slide, I showed spatial bias, but this slide really shows how much we have a temporal bias. So what these plots are showing, it's a cumulative plot, all of the data broken out by igneous and detrital, right? And so all of the data for igneous, for example, for the different continental zones. So let's take an example. So in the late Archean, early Paleoproterozoic, if you just look at the igneous data and you say something about the global record, you're saying something mostly about the Asian continental zone, right? There's not a lot of North America in there. There's not really a lot of African data in that part of Earth's history, right? So again, it's a bias. And so look at the detrital record here. So say you're really excited, I don't know, about the Neoproterozoic. Well, look at the Neoproterozoic. How much data do we have from Australia? Basically zero, right? And so is this a global record? And I would argue that, say, no, I don't think it is. I think it's a biased record, both spatially and temporally, right? Because here we have a lot of Antarctica data, which is great. Data from Africa, those Peri-Gondwanan terrains, but Baltica, North America, they kind of drop off in terms of data density. And so it's a biased record. So here are the bivariate kernel density estimates. There's a lot on this plot. So again, I'm going to take this slowly. These are bivariate kernel density estimates for each of the different continental zones, right? And so again, it's a story of bias. Look at how much data comes out of the Asian continental zone versus even compared to North America, right? There's, what is that? At least about 3 times as much data coming out of Asia. Sorry, there's something going on out there. You can hear the sirens. So the interesting thing about these plots is, well, they're completely different, right? So if you look at the African versus, Baltican signals, they're completely different. And this really, I don't really find this terribly surprising, right? So in Baltica, you have this latest Paleoproterozoic, the Mesoproterozoic peak that's, it's sort of juvenile to intermediate. But if you look at the African sort of data density, we have a big smear here, all the way from juvenile, all the way down to very evolved, what I would call highly evolved. And that highly evolved signal is It's present in Africa, it's present in Antarctica, Australia. North America is this is actually a little bit later, Peri-Gondwana, but it's not there in all of the trains. It's not really there in Baltica. It's not really there in North America, right? So this is very telling. What we can do is relate each of these peaks in data density to, we can go into the literature. Again, I'm coming to geoscience from a very Cenozoic centric kind of point of view. So you go into the literature and say, hey, there's a big peak in data density in South America. What's going on there? And you find that it's a formation of the Amazonian craton, right? And you can look at pretty much anywhere. The Grenville is a great example. So you look at the Grenville, this huge peak in data density. If you do detrital work, the Grenville's probably in your samples, right? It's everywhere, right? But what you can say with this sort of plot is, that's actually pretty juvenile, right? So that's plotting pretty close to that depleted mantle. And you go look at, you dig into the research that covers the Grenville, and say, hey, that's, follow Chris Spencer's work. You say, hey, that, this is an external kind of origin in the verbiage of Collins 2011, right? And so that makes sense. It's analogous to, say, the external origins that we have today, like the Pacific Ring of Fire, right? So you would expect that the chemistry would be more on the juvenile side rather than the evolved. And so this can be and as I was using it early on, this is a nice exploratory tool, right? This is a weird looking plot. So again, I'll spend a little bit of time on it. Basically what I'm doing here, so I'll go back one. I'm going to compare every continental zone to every other continental zone. So compare Africa to Antarctica, to Asia, to Australia, Baltica, and so on. And what you get is something around 25, 26 individual similarity maps, as I showed before. And what these show is the warmer zones. I know these are very small plots where you have peaks in density. These show a shared age and hafnium chemistry for whatever comparison that is. So this one, for example, would be Australia versus Baltica. And this one, for example, would be North America versus Baltica, right? And so it shows where they're similar, right? And this is a completely objective way to analyze and try to interpret these data. And so, and it's similar to if you've ever looked at a bivariate or a, what do they call it, pairwise comparison matrix of numbers. It's sort of the same thing, just with these little maps. So what Francis and I did is we said, well, let's make these plots and let's go looking all the way back as far as we can in terms of paleocontinent interpretations. See how far back we can go. So here's some work showing Kenor or Kennerland, where the deeper you go back in time, obviously the fuzzier things tend to get, right? So we don't really have a ton of information here, but we do have this new tool, these maps, right? And so this reconstruction shows that we should have, we should predict maybe a shared chemistry there between Baltica and North America. Perhaps Australia, Africa might be on the map. And so where are the peaks in similarity? So indeed, we have North America and Baltica, right? So that's a nice, confirmation's the wrong word, but it's nice to see. Africa, so Africa does have some shared similarity with Baltica, right? This box right here. And interestingly, South America isn't even on this, this reconstruction, but there is a peak in data density there in comparison to Baltica. So now you can start hypothesizing, right? So this exploratory tool then leads you to hypothesis-driven research, which is pretty exciting. So we moved on to, I'm just going to step through sort of 5 kind of supercontinents that I'd say most people agree on. Not everybody agrees, certainly not on the configurations. But moving forward in time, Nuna was just measuring some belt rocks a couple of days ago, so a very exciting time for me. But here, you'd predict that you have maybe shared chemistry there, and lo and behold, you do, right? So North America, Baltica, and Australia, we see major peaks in data density, rather similarity, right? So that is a pretty exciting result. And you go through these different maps and you can find the same time, say the Asian fragments that are kind of floating around there compared to North America, there's no peak in similarity there. So again, this exploratory tool is a nice test. Move forward into Rodinia, so the picture starts to come together a little bit better, but still Rodinia, that's still pretty deep time. And you can make similar predictions. So you find North America, Baltic, Australia, and Antarctica are kind of the major players here. And on this particular reconstruction, a recent one from Ding, there's no Antarctica even on this map that I'm seeing. So so then you can start to test some of these reconstructions, these paleogeographic reconstructions. So here's Gondwana. So I'll talk more about Gondwana as we move on through this talk. I'll sort of start to focus on Gondwana. So Gondwana is sort of parked down at the South Pole here in this particular reconstruction. And the major players are the ones that most agree are part of Gondwana, right? So Africa, Antarctica, South America, and so on. And you see these major peaks in data density associated with that. This is a Precambrian forum, but let's throw Pangea in there just for fun. And you find some interesting results here too. So I'm just gonna kind of skip over that just for the sake of time. One of the conversations that Francis and I had right after lunch, actually, when we first met, is I told him about this sort of idea. I'm like, hey, when you sum all of these comparisons together, what falls out of it is the supercontinent quote cycle, right? And this is I think this is a really kind of interesting and telling plot. So basically you sum together where these maps are similar, right? And you get a different picture than if you just plot all of the data. And so the major similarities are these sort of warmer colors, these major peaks, right? And interestingly, and there's a little one right here, these tend to precede the interpretations of supercontinent tenure, right? And I think that makes intuitive sense, right? So imagine you're amalgamating a supercontinent. When are you going to have the shared chemistry, the orogenesis, the magmatic activity? That should happen before the tenure of the supercontinent. So during supercontinent amalgamation, you have shared chemistry, and then supercontinent tenure and subsequent breakup, you don't see that similarity in between. So again, this fell out of exploratory research, but now we can start making hypotheses with that. So that's a pretty exciting result from our work. So you've seen this plot already. Now what I've done is I've added the uranium lead data to it. So before, these are the same bivariate kernel density estimates, right? So here's the 44,000 from Asia, the 15,000 from North America. There's a lot more uranium lead data out there. And again, Steve Putz is the one who really put the geographic coordinates on this. And look at some of these numbers. So 105,000, North America has even more, so 134,000 individual points. I think there's, he's pushing 1 million in the database. Last I communicated with him. So this is work in progress in terms of the database and in terms of it's basically how large it's getting. And the point I want to make here is that you get a different result if you only look at the uranium lead versus the bivariate hafnium data. And to do this, let's focus in on that latest Neoproterozoic and pushing into the early Cambrian and a little bit into the Ordovician. And so these are a little smeared, probably should use a narrower kernel bandwidth, but it still gets the point across for these different continental zones. Within the latest Neoproterozoic, the data density is different depending on where you're at. So you look at Africa, so you have a major pulse in very juvenile hafnium early on, and this major pull down almost right at the latest Neoproterozoic boundary. Compare that to Baltica. There's not a lot of data coming out of Baltica at this time, but you don't see that major pull down. Same with North America. It's sort of there, but it's not as strong as, say, look at Peri-Gondwana terrains and certainly Australia, right? So what we can do, we can use this quantitative comparison tool where we compare each of these in a pairwise sense. So just as we did before, we compare Africa to Antarctica to Asia. And instead of showing the little maps like I showed before, I'm just going to boil it down to a number. Right. And so here's a pairwise matrix where you sum that similarity. And the nice thing about a pairwise matrix of numbers is you can make a multi-dimensional scaling plot. And for folks who don't think about these all the time, like I do with detrital work, what this shows is the closer you are to another data point, the more similar you are. Or if you're very far away, the less similar you are. So this plot using only the uranium lead, this is UPB only. You get basically a non-unique result, and it shows one that I think is a little suspect, especially when we compare it to the hafnium data. And so I'll highlight here is that when we make a multidimensional scaling plot out of those data, you can see that we clearly separate out the Gondwanan terrains and non-Gondwanan terrains. And the uranium lead and only versus uranium lead plus initial hafnium, you get some very different results, particularly with North America compared to, say, you go North America compared to Antarctica, North America compared to Australia. Right, so just another way to use this, this quantitative tool. And there are other metrics, cross-correlation, likeness, and some other ones that I'm not going to talk about. Okay, so let's return to the database, and this is really going to kind of bring this talk home. This is now moving into work that Francis and I are currently working on. And so here's the database again. Now what we're going to do is completely ignore these boundaries. I'll keep the colors on there just to help guide the eye. You start rewinding back in time with reconstructions, it's easy to lose terrain. So I'm going to keep the colors the way they are, but I'm going to take these data and put them into G-plates. G-plates, it's pretty new software for me. I've been aware of it for a very long time. It's been an absolute blast. It's certainly probably not a new thing for anybody in this crowd, but for me, it's pretty new stuff. So I'm extremely excited about using this. So what we did, we took all of these data points and tied them to individual plates using the G-plate software. And this is a little GIF that I made. And basically what we did is we hit rewind until we get to the latest Neoproterozoic. Right, so you see there's Pangea, live and well. The way we set up this problem, this is extremely preliminary, right? So if the plate disappears, and this is a plate model from Andrew Murtath's recent 2021 paper, those folks, if the plate disappears, the data disappear with it, right? So you notice in here, like Africa's missing a whole bunch of plates. We need to go through and quality check a lot of these. This is what we're working on right now. But if we rewind it back to 550 MA, we can clearly pick out Gondwana, right? And continental zones associated with Gondwana versus not Gondwana. And then extract that data from this reconstruction and see if those signals differ. Because again, the hypothesis be for some folks is, okay, well, is this an Earth process, a global Earth process, right? And if it's a global phenomenon, say related to say snowball Earth or something, these signals should be similar, right? And so non-Gondwanan continental zones, no real surprise here. There's just not a lot of action in that part of the reconstruction. For igneous only. Now detrital grains are finicky, they move around, you have sedimentary recycling and so on. But even with that, you don't get this major pull down that we see in the database at 550 MA. Interestingly, we don't really see it in the igneous record of Gondwanan fragments, right? So we have Gondwanan terrains and the data associated with that. And so we really don't see it there either, which is actually back at the Vegas meeting, I gave us a short version of this talk and I redid the analysis and I put these plates back in there just to test this, like what are we missing? And it looks very similar. So it's really not there. So basically undiscovered, or he wrote it away, who knows? Where that pull down is alive and well is in the detrital record in Gondwanan continental zones. So that's really where this global pull down exists, right? So if we take all 4 of these plots and sort of just compare them, so I'll just draw a line here in between. So the top is non-Gondwanan, the bottom is Gondwanan. And there's that pull down that I was so excited about when I first saw it in my Cenozoic Andes data, my detrital data. Okay, so at the end of the day, again, I think it's a cautionary tale of spatial and temporal bias. So here's a nice reconstruction from Ben Gascami's work in 2020, a couple of papers that year. What I'm going to do is take this reconstruction and just simplify it. And it's very bright green. So here's Ediacaran Cambrian sutures and simplified continental zones. So India is one of these Peri-Gondwanan terrains as we've defined it. And so what we can do with this database, because of the way Steve put it together, we can actually go through and look specifically for that signal. So we can parse the data in yet a different way where we say, okay, I want the most negative hafnium within certain bound, right? So take all of the Ediacaran Cambrian data, just delete off everything else and find everything that's at least 30 epsilon units negative of that depleted mantle line. And we'll call that, quote, highly evolved. Right, so we're looking for the most evolved. So again, this is all highly evolved data only, and only in this age range. And this is just the detrital data, right? And so here's a bivariate density estimate again, and it shows where these data exist. So we have a major peak or major mode in data density in Asia, South Australia, South America, and only a handful of points in North America. One just kind of floating way up here. But this is a bias signal where we actually have these highly evolved zircons that people have found and analyzed. And they correspond quite well with Gondwanan origins, right? Gondwanan sutures. So we have the East African origin here, the Kunga Agassi origin, South America. So this is a primary source for those Andes data that I was talking about earlier. How did they actually get way out there? You know, that's a big question for me. But we can find them, these highly evolved grains associated with Gondwanan sutures. And if we look at the igneous records, so here igneous only, these show a couple of primary sources. One of the biggest ones is in West Africa, right? And so that is associated with this guy right here. It's out there in West Africa. And then the southern tip of India. So these high temperature kind of granulitic rocks down there, a major pulse in the database. So again, this speaks to a spatial and temporal bias. So if you interpret this major pull down in the absence of geographic and geologic context, I think you're going to have a very biased result. Rather, you'll be saying something more about, in this case, for the latest Neoproterozoic, you'd be really talking about Gondwanan sutures, right? And that's where I'm going to leave it. So I think I saved enough time for questions. Looks like it's about 10:49. So, so to conclude, bivariate kernel density estimates, I think these are an incredibly useful way to interrogate not just uranium lead hafnium data, but really any sort of bivariate data. So if you have trace element data that you're struggling with scatter plots, make a bivariate kernel density estimate out of it. It'll really help with interpretations, objective interpretations, especially. Hafnium and zircon is, it's a product of its tectonic environment. I think you can look at hafnium data, even from a detrital sample, say you have no idea where these grains came from. If it's very juvenile versus very evolved, I think you can, at a first, maybe even 0th order, you can start to talk about its tectonic context, right? Global records of hafnium data, initial hafnium data, these are, I think these are incredibly biased, right? They're dominated by regional orogenic events that are then modulated by the amalgamation, tenure, and breakup of the different supercontinents we've had in Earth history. And finally, the latest Neoproterozoic hafnium excursion it's limited to continental zones associated with the Gondwanan supercontinent. And I think it's difficult to make a case for it being related to some sort of global Earth process. All right, with that, oh yeah, I'm gonna draw all over this. So definitely a huge thanks to George. He's an amazing mentor. I still work pretty closely with George and the Arizona Lasercron crew. Really, there's no bounds on what kind of research I did during my postdoc, and this was completely out of left field for me. And so it's been an absolute blast, and I'm super excited to continue doing it. Folks that have published their metadata, published their data in general, so that guys like Steve can go and put them together into a monster database that we can all access. If you're interested in this database, I have it. It's on my GitHub, and the version, the way that Francis and I parsed it, at least. And of course, nothing happens without money, it seems like. So big thanks to NSF. So NSF supported me as a postdoc on the Lasercron grants, and then Francis has several grants that he's been working off of. So, and a shameless plug for the paper, got to do that, right? So here's the paper. It's out in EPSL. This was a long time coming for me and Francis. So very excited that it's out there and hopefully getting read. So with that, thank you so much. And again, thank you to the UCR folks for letting me fill in for this talk. This was fun.
Thank you, Kurt. It was great. We open it for questions, and we actually have one that was sent directly to me, but I copied it to everyone else. So I'll read it, and maybe it's from Gefa Kartfuk Morari, and maybe this person can expand on it and explain better the question. But the question, there appears to be increased number of igneous zircon in China and Central Asia, but where appears to be abundance of sedimentary zircon in South Africa. Any particular reason for this, or is this just an artifact of sampling bias of detrital zircon? I don't know if Kurt's question makes sense to you, or do you need Gefa to explain it better?
Yeah, so let me go back to a slide that has, now it's gonna have a lot of drawings on it, but yeah, I think I understand the question. So really the question is why? Like, why do they dominate so much? I'm gonna go back to way back here. So this is, this shows igneous and detrital combined, but it still gets the point across. I think it's a couple of reasons. One, there's been a lot more work done in these parts of the world. So you can imagine, when you analyze an igneous rock, you don't analyze hundreds of hafnium points, right? You analyze just say, I don't know, 20, 30, and then you figure out the chemistry and you move on with your interpretation. With detrital samples, some labs are doing hundreds of these analyses, and for work out in China in particular, especially out in Tibet and then China kind of proper, it's there's just a lot more data, so it just kind of overwhelms the database, right? So that's one thing. The second, it's and we talk about this in the paper. It's really and it's Hawksworth talks a lot about it. It's a question of preservation potential, right? And it's something I think a lot about in sedimentology. Like, how likely are you to preserve these detrital grains, for example, on the interior of the continent versus where the orogenesis is actually happening? So the interior of the continents versus the where the origins are actually taking place, where the orogenesis is taking place, you're going to have a different abundance of grains, right? So it speaks to bias. Where are the suture zones? Where was the orogeny? Where are you sampling, right? And so part of its preservation potential, and the other is just how much data is being produced in these different places. There is a pulse here in Western North America, a lot of work out there, but nothing in comparison to the amount of data, say, out of South Africa. So yeah. How much people are running analyses, what people are excited about publishing, and what's even preserved.
Okay, great. So next question was in chat room to everyone from Lyle Nelson. Lyle, do you want to phrase your question, or should I read it?
Sure, I can. I don't know if my internet's very good, but if you can hear me. I was just asking, it makes sense, given the data you showed, that the 550 negative excursion is Gondwanan biased, which makes sense if that's where all the arcs and subduction zones are. But you didn't get into whether you think it could still potentially be driven by a sediment subduction signal, and if that's not the case, what that negative excursion is driven by. You mentioned at the beginning this idea of internal origins, but I was wondering if you could speak a little bit more to that.
Absolutely. Yeah, so here's my little drawing. We have a better version of this in the paper. This is what I had on hand. But absolutely. So kind of you think about what's the recipe for that any pull down really. And yeah, you have to have the old zircons sourced from some very old terrain, right? But you also, it's a mix, like I talked about George's sort of Libra, right? If you have an intervening ocean basin that's expansive, that's very wide, that's going to be mixed in with the melt that's formed that incorporates these old zircons, and you'll start to pull that toward more juvenile. You might land in some intermediate zone. So I think what's critical is the absence of any kind of wide intervening ocean basin, right? So I guess to answer your question directly, absolutely. I think that the sediments that look at the paleogeographic reconstructions, the sediments that were being shed into the oceans, they were coming from these very old, this old continental crust. But I think it's, again, critical. And so yes, it can and probably did result in that pull down, but it's the absence of that intervening ocean basin that's absolutely critical. Hopefully, Lyle, that answered your question.
Yeah, just given that, then how do you test it? It doesn't seem like it nulls the Keller hypothesis of there being more sediment input from erosion. It just provides another source of sediment just from the rifted margins, and that it's becomes difficult to test, it seems like, those two possibilities. Absolutely.
And it's something that we wrestle with quite a bit. I think a couple of things that I will say. So if there was, they talk about like the 3 to 5-ish kilometers of basically beveling the continents and generating the great unconformity, but that's from all of the continents. If you did that to North America, it's a Laurentia and all of that's kind of floating off closer to the equator in most reconstructions. But if you were to subduct that, what were the trains that were being eroded? They were probably a lot of Grenville, right? And so Rodinia. And so Rodinia and Grenville grains. So you would get intermediate kind of at best, because Grenville is mostly juvenile, right? Those zircons are. And so it's a spatial sort of test in that sense. So, is it every continent? But then there's the time aspect. So when was snowball Earth versus when you have this major pull down at 550? That there's a lot of time in between that, right? And so you would presumably have more of an intervening ocean basin, right? More juvenile crust that you would incorporate, and again, I think that would pull you right back up. This is the test. Really, is it this global sort of signal? I think it's just localized to Gondwana. Yes, with subducting and melting the tridal zircons, but it's where did they come from and when. So if the Keller hypothesis works, it has to be sourced from snowball Earth erosion, right? And on all of the continents. And if you did subduct those zircons, I think you would get a more intermediate at best signal.
Yeah, so I guess but why, when there's other times in Earth history where you have internal origins, and why do you not see as big of a negative excursion then?
Absolutely, yeah, that's a good question. It's really what terrains were being melted, right? So again, it's either a passive margin, detritus, or it's the continental crust itself. I think the configuration of Gondwana was kind of like the perfect storm, right? As I kind of think about it, of a lot of old crust coming together. You look at, Nuna is analogous kind of to Pangea, where you have sort of this uptick in more juvenile, but then you look at, Rodinia, you get more juvenile because you're sort of looking at external orogenesis, and you kind of turn that thing inside out, as some have suggested, and then you basically amalgamate all of the older fragments. Again, I think of it kind of as this kind of perfect storm of old crust and erosion of that old crust.
Thanks. So just following on the same question Lyle asked, so there are other regions like in Baltica, in Urals, or in Siberia with about the same age, late Neoproterozoic, early Cambrian. So basically you explain all of them by subduction of old oceanic crust, and also to initiate subduction, I guess you need some time before oceanic crust get sort of dense and could be subducted.
Sorry, I wanted to get to here. Not sure I completely follow. So
it's like there are other origins of about the same age as in Gondwana, like in Baltica or in Siberia. And I guess your response to it would be that these are subduction of old oceanic crust. I presume that would be the reason why they don't show negative epsilon hafnium.
Yeah, it's all about what's incorporated. To get a more negative epsilon hafnium, you need to incorporate older zircon, right? And so what was being incorporated in, say, Baltica here, right? So you're not incorporating, really there's just not a lot of activity at that time anyways in Baltica, which is an issue in itself. But what you are melting, you're not melting, say, Archean Paleoproterozoic zircons, you're melting something else, either your primary input from mantle or young continental crust or younger detrital zircons. So the recipe really is you need those old zircons, because if it's true that most hafnium is locked up in the zircon, then you need the older zircons to bring it down, right? To be incorporated in that melt. So they're just not there, would be the quick interpretation.
And maybe I missed you mention that during amalgamation of supercontinent, you would have sort of most of the signal in epsilon hafnium, I guess negative signal, whereas during tenure and rifting you will not. But it seems like during rifting you would also be melting all the continental crust. Maybe I missed your point.
For rifting, yeah, but again, it's what is incorporated, right? So if you think of lithospheric extension, the kind of classic Mackenzie model, you're going to incorporate a bunch of primary mantle, and that's going to bring you more toward the positive epsilon hafnium, regardless of how much older, more evolved zircon you incorporate, right? So you land somewhere in between. It's like what's put in the melting pot, right? So I kind of think of it in a very kind of abstract sort of way. So you hit on this point. Let me run through these real quick. So the similarity taking place, most similarity, the peak similarity of these modes preceding the tenure. I think that's an important point in its own right. But I guess what I was trying to answer one of the last questions, how evolved are the different supercontinents, right? So you look at this one right here. Look at how juvenile that is compared to this latest Neoproterozoic amalgamation, right? And so I think that, again, thinking about Collins, the seminal kind of 2011 Nat Geo paper, I think that really starts to speak to internal versus external orogenesis, and you dig into the literature, and it seems to work pretty well, right? And it's actually kind of this alternation, right? Up, down, up, down, up, down. It's interesting to me, whether it's actually cyclical or it's just, I don't think of it as a cycle. It's just a pattern that these go through. Like you amalgamate, sit there, and then they break apart. But what was incorporated during the amalgamation, I think, is an important point. And so, like, you have here external and then in internal.
Thank you. Okay, any other questions for Kurt?
Felix and then me.
Oh,
yeah.
Yeah.
Can you hear me? Can you hear me?
Yep.
All right.
Yep.
Because I had problem with my computer yesterday. So thank you very much for this great talk and opening some interesting ways to treat bivariate data. It's very interesting. Thank you. I have a bit of, perhaps you said it at the beginning, but the data the original data, they're from the actual continent, right? So you didn't, because the more back in time you get, the less likely that what you're looking at was part of the actual continent. How did you deal with that problem? For example, maybe if you look at if you took a sample from the Appalachian in North America, well, during Grenville time, it was not part of North America. So how did you deal with this problem?
Right, and especially this is a huge problem for the detrital data, right? Because those grains like to move around. So part of the work that I did, the paper that introduces the method for comparing bivariate data, one of the tests we did, we took these the same kind of configuration and we compared South America igneous versus South American detrital, and generally, the big kind of punchline was, the detrital is pretty much pretty representative of the igneous. It's kind of like like if you do detrital zircon work. But more specifically to your question, yeah, you look at the Grenville, where in the Grenville, right? If Grenville sits in the Rodinia, it's not like specifically part of a continent. I think about North America, but this thing's expensive. This is where Francis and I really had to make a tough decision of using Paleozoic sutures. We're most interested in Gondwana for this work at first, but you kind of just have to make a call, right? And so it's the perfection is the enemy of progress or something like that. This is kind of a coarse first test. I think a better test is where we're going with it, with the G plates reconstructions, because as I mentioned with the G plates, yeah, the colors are on there, but we don't ascribe like, okay, we're going to make this a hard boundary, or we're going to make this a hard boundary and everything east of the Urals, we're calling that Asian. We're not doing that in the G plates reconstruction. So we're maybe taking it. Go ahead.
So a data point listed in your talk and in your paper is a data point in the actual continent.
Yes.
Okay, perfect.
And so where we're going with this, you take that data point, tie it to a plate. For detrital records, that's an issue, right? Because they move around. For igneous, I think it's quite robust. The problem is there's obviously far more detrital data than igneous. So, but it's a first step, right? And so by just demarcating these zones based on Paleozoic sutures. Now taking the next step with G plates.
Yeah, you have to start somewhere.
Yeah,
And
you gotta start somewhere.
If I can ask well, maybe Paul, and then if we get time, I would have a second question.
Sure.
Okay, so I find the juvenile nature of the Rodinia age zircons to be somewhat surprising, because most of the major Rodinia forming orogens border Archean cratons, not over their entire extent, but over significant parts of the extent. So consider the Grenville orogen borders the Superior Craton, Namakwa Natal borders the Kopfal, Kibaran borders Zimbabwe and Tanzanian cratons, Eastern Ghats borders the Darwar, Bastar, and Singwum cratons, and the Albany-Fraser belt in Australia borders the Yilgarn Archean craton. So there's no requirement, of course, that the zircons involved in those orogenic belts were derived from the Archean cratons, but if they weren't, it raises an interesting question. And I don't think it's satisfactory to me to say that this fits the external versus internal, because when you look at the geological map, it doesn't actually seem to work that way.
Definitely, and to package it into the Collins 2011 sort of model is definitely broad brushing it. No question about that. I start thinking about preservation potential, or what was there more of? Yeah, these different zones were adjacent with a very old continental crust, but what is dominating the database? I can go in and probably find a lot of those more evolved parts of the database, but what is kind of swamping the database? And I think there's just more of the juvenile stuff. So when you start to, even at the level that we're parsing this database down into smaller and smaller and smaller packages, we're still biasing there, right? Because you have to eventually call it somewhere. Where are you going to how are you going to parse the data? You got to put walls on it somewhere to move forward. But I bet they're in there. I haven't looked in that level of detail. There's a lot of data out there. So
is there a statistical way of evaluating how biased geographically the data are by, say, simple clustering, geographic clustering? I know that doesn't work so well for the detrital, but still might work a bit.
Yeah, because
it looks to me like there's a lot of data from Tarim.
Yeah, it's a ton. Where'd that plot go? This is the similarity sum, but it shows very similar where the densities are. Yeah, there's actually, if I go back spatially, I still think this is one of the most telling plots. Yeah, it's a bunch from out there, and this is detrital and igneous. But when you parse out igneous versus detrital, you get a similar picture. It's in the paper that I published with my former PhD advisor. It's the methods paper for this. So we do tease that out, and you see a similar thing. You see these big peaks in data, these big modes in data density. But if you drill down into the database, I think you would find some of these other kind of smaller, well, not small, but these terrain boundaries that you're talking about. And it's actually pretty easy to do. The way we published our supplemental, I tried to make it as easy as possible to go in and to sort in different ways and to pick out individual individual origins or zones or regions that you're interested in. And actually QGIS is probably the best way to do that. ARC is pretty clunky for this much data. So if it's an easy test, right? To drill down and find those. And I bet they're there because people have probably done Hafnium on those rocks.
Thanks.
Yeah, definitely.
Yeah, Felix, go ahead.
I'm very interested in your pairwise comparison that was up just before when you were talking, when you were answering that question.
Oh, which slide?
For the Rodinia pairwise comparison.
Yeah, so not the nuts and bolts, but the actual data.
Yeah, when you have all the pairwise matrix.
Yeah, so this guy.
Yeah.
That's a lot.
Yeah, but did I see correctly that when you compare North America with South America in the Grenvillian time, the correlation is relatively weak.
So North America versus
This
South
one
America.
here. Yeah.
This guy. If I could just zoom in on that. During Grenville is pretty weak. Yeah, and you know what I think is, these are all relative to that comparison. What's happening here is it's just dominated by that major mode right there.
I see.
And so it's, you see it, you know, it's in there as I like scribble all over it. I bet you can, and something you can do with this comparison, you can just truncate off the older and younger parts of the age range. And I bet that brightens right up. So these are all normalized to the highest data density in the whole, like all of them. And that highest data density, if I remember right, is South America and Peri-Gondwana. And so that one is, actually that is that, so that's just dominating. South
Okay,
America.
that answered my question. Thanks a lot.
Yeah. So they're all relative. Oh no, it's actually, that's the highest peak right there. And so everything's normalized to that. So if you just take the raw results in the code and the software, that'll probably brighten right up. Yeah, they're all relative. So that's something you wrestle with, you know, these sort of ad hoc quantitative methods.
Okay, good. Any other questions for Kurt? Let's see. I don't see any other hands. If I'm missing, unmute yourself and feel free to ask.
I'm looking for hands. I don't see any. Oh, hey, Paul. There you are. Yeah, I'm not seeing any hands either.
Okay, I think we'll let Kurt go. Thanks, Kurt, again for doing it on a short notice. And we all reconvene in early September, and there is already a list for the rest of the year. And in late September, we will start asking people to talk in 2023. So enjoy field work and see you in September. Thanks, everyone. Bye.
Thanks, Alex, Andre,
Yeah.
everyone.
Thanks for doing this.
Greg,
Thank you, everyone.
Bye.
I sent my manuscript in, Daryl.
Yeah, I hope you, I approved it. Have you got any feedback from that?
Not yet.
That was last week. So Sally may be taking a lot of time in believing what I've written about it.
I got another gift for Brendan coming up.
Okay, well, see you
Thank you,
next
Daryl.
time.
Yep.
Bye, everyone.
Bye, Kurt.
Thank you again.
Francis.